Thanks for coming. This is a session on network security for apps running on OpenShift Container Platform. Quick question before we get started. Actually, let's introduce. I'm Veer Muchandi. I'm a principal architect working for Red Hat. I work on OpenShift Tiger team. And this is...
So me and Veer works in the same team. My name's Shanna Chan, Senior Solution Architect. So he just explained what I do.
Yeah, so we both go and help our customers in adoption of OpenShift Container Platform in North America. So we have worked with most of the OpenShift customers who have adopted OpenShift so far, right? So we get them started. We do education sessions. We do proof of concepts, deep dive sessions on specific topics and things like that. One of those topics is this one. So this session is a little advanced. It's not an introductory thing. So there is an expectation that you know at least the Kubernetes concepts like pods, services, and all that stuff, right? So how many of you are using OpenShift? Can you? Perfect. That's almost everyone. That's nice. All right. So let's get started. Agenda for today. This is going to be a packed session in terms of the amount of information that you'll gather. So be attentive because I'll be going pretty fast, unlike what I generally do. This first we'll go with an OpenShift SDN overview, which is software-defined network that comes with OpenShift. And after that, we'll get into typical scenarios. Some of these scenarios might apply to you. These scenarios are derived based on the kind of questions that Shauna and I get asked on a day-to-day basis. So we'll talk about a scenario, the kind of questions that we get asked, and what solutions do we have in OpenShift, or how do you solution around it for OpenShift, right? That's the topic of discussion. So first, OpenShift's SDN overview. OpenShift uses Kubernetes CNI, Container Networking Interface, right? That's the standard using which we plug in OpenShift networking. The thing that you see in green here, which is the OpenShift plugin, right? That is OpenShift's SDN. It's based on a technology called OpenVSwitch, just like everything that Red Hat does. OpenVSwitch is an open source project, which we have called it as OpenShift's SDN. That's fully tested. It is supplied with the platform. When you install OpenShift, SDN is included. You don't have to do anything with it, right? However, in case you are interested in any other networking technology, we have a bunch of partners, and all the things that you see in blue here, like Flannel, Nuage, Calico, Contrails, Contive, any of these things, right? These are all validated plugins, so you can remove OpenShift SDN and use the other plugins if you wanted to, right? And there are other plugins that are under development, which is OpenDaylight. So CNI is that standard which allows you to change these networking components as you desire. There is no specific favorite or anything, but we supply this so you can use this by default. But our rest of the conversation is going to be focused on OpenShift's SDN, not the others. Now, OpenShift's SDN comes in 3 different flavors. SDN itself creates an overlay network. It creates a VXLAN network on your physical network, right? And it comes in 3 different flavors. When you set up OpenShift, or even later, you can change it among any of these. The first one is OpenShift, the OVS subnet configuration. With OVS subnet, you get a flat network across all the projects. So if you are running pods, any pod can talk to any pod when you run them on OpenShift. That's OVS subnet. This was the default that we started off with. Later, we introduced a second plugin, which is a second type of plugin, which is OVS multi-tenant. What does multi-tenant allow you to do? It allows you to create one network per project. You know, OpenShift project and Kubernetes namespace are same, right? So it allows you to create one network per namespace. The way in which it does that is every namespace gets a virtual network ID, and all the pods that are within that project get the same VN ID. So pods with Same VNID can talk to each other. Pods with different VNIDs cannot talk to each other. That's how multi-tenant will work. The third type, which was introduced about 6 months back, is OVS network policy. This allows a finer grained control. We'll talk more about it a little later. Let's understand how this OpenShift's SDN works. Since most of you are using OpenShift, you know that there is an etcd, which is the data store where the entire configuration about your cluster is stored, right? Part of that etcd is a node registry. And that node registry is the place where the network-related configuration gets stored. So as you add a new node to your cluster, master allocates a subnet from the list of IP addresses that you would have supplied, right? Whenever a new node gets added, it takes a part of it, a subnet, and it allocates that to a node. If you remove a node from the cluster, it removes that from the node registry. So the node registry is the place where the list of subnets allocated to each node are saved, right? Now what happens on the node itself? When you add a new node, OpenShift's SDN sets up a bridge network. So this bridge network has 3 different parts of it. The BR0 of this bridge network, OVS bridge, gets configured to talk to any pod on their ETH0 interface. On the other hand, there are 2 other ports that get opened. One is a VXLAN 0 network. So any traffic within an OpenShift cluster, if a pod A is talking to another pod, and if that other pod is on a different node on the cluster, that traffic flows through this VXLAN 0. If you are talking to anything outside OpenShift, that traffic flows to ton 0. Okay? Let's see this in a little more detail. So OpenFlow rules are added to watch this kind of stuff. So whenever you create new nodes in your cluster, when you add new nodes in your cluster, every node in the cluster knows about their brother now. We have a new brother, so this is added now, right? If a node gets deleted, every node in the cluster knows about it. And the OpenFlow rules are set up in such a way that, hey, if I get a new pod with that IP address which is on that subnet, I need to redirect it to that particular node, is how the VXLAN rules are set up. Now, whenever the new pod gets created, it assigns one of the IP addresses from the subnet that is given to the node. So node gets a list of IP addresses, right? From those list of IP addresses, one of those IP addresses is allocated to the pod. And this ETH0 is mapped to that BR0 network, right? And OpenFlow rules are created here so that if traffic comes in, what do I do with it, right? In case we are setting up it in that OVS multi-tenant mode, let's say, then the rules, the OpenFlow rules are created in such a way that if the traffic is coming with the same VNID, it is allowed, otherwise it's not allowed. Those configurations are taken care of, right? Next, how does the traffic flow? Let's say we have a pod A that wants to talk to pod B. And when the request goes out, it goes from the ETH0 and it reaches the OVS bridge. If these 2 pods are on the same node, let's say, right? It goes to the OVS bridge and the traffic is addressed to this particular IP address, right? OVS bridge knows that, hey, this is within the subnet. So it is within my same subnet. It's on the same node. So based on the OpenFlow rules, it redirects the traffic immediately to the other pod on the same node. What happens if pod A wants to talk to pod B, but pod B is on a different node? So traffic goes out to BR0, right? Based on what I just said before, every node knows about every other node on the cluster, right? So since the traffic is addressed to a different subnet, here you see the 2 here, right? So the bridge network here knows, based on the OpenFlow rules, that it is directed to a different node. So it sends the traffic via VXLAN 0, which goes over the overlay network, reaches the other node. There it goes again to the bridge network, and here it finds the pod and sends it there. Very simple, right? Next, what happens if you have to if your pod is trying to talk to an external system? The flow is the same. Here at the bridge, it knows that, hey, this IP address is not on the OpenShift cluster, so I have to send it outside. So it redirects the traffic to port 2, which is ton 0. From there, it gets natted, goes to the physical ETH0, and then gets out. Right? This is how the OpenShift's SDN works. Brief introduction. Now let's talk about different networking scenarios and what solutions we have. The first one, how do I restrict traffic across tiers? Let's understand this a little bit more. So usually, when traditional applications or applications that we have been building so far, right, they are divided into different tiers: presentation tier, application tier, database tier. So when a presentation tier typically calls application tier calls data tier. This is all known, right? And certain connections are not allowed. So your presentation tier should not be talking to the database directly. So how do I set this up on an OpenShift cluster? Like, how do I take this kind of an application and restrict these kind of accesses on an OpenShift cluster, right? That's where network security policy helps. So remember the third kind of plugin that we talked about, OVS network security? That's the one that you want if you have this kind of a scenario. What it allows you to do is goes over and above what we discussed here. It is not just this, it also allows you to do microsegmentation. You can control the traffic going into pods at individual pod level, not just at the tier level. You can exactly say that, hey, from this pod, I will allow traffic to this other pod, and also I'll allow traffic only if it comes on specific ports. So you get microsegmentation at a very granular level. Let's look at an example of how this is done. So when you look at the example, it will be at this demo next, you'll understand it better.
So we're going to have a system, a sample like this, like any applications that might be similar to what you have. This application, it would be simplified in a simplified form, that you have an application that have multiple services behind the scenes, and you have your services in different namespace projects. You see project namespace, as Veer mentions, they are similar. And by default, pod and pod communication, they can communicate freely. My pod PHP can talk to my Node.js PHP across namespace. But then a lot of time we want to restrict the access, how the application, the traffic flow through the applications. We might not want everyone talk to each other, or we want some kind of security for the backend service. So before we do that, let's take a look at my application if it's working before we get started and see how that get implemented. And this service is very simple. I have a PHP application, and then we'll call the backend to do registry, save the information in it, and then we'll send an email to the new user who registered. And then it will be able to log in and get the info of that user, and then we'll send another API request to the treater service, and then we'll pull the treat and then show up on the screen. So looks like my application is working. But then now I could have a PHP file that actually be able to just directly hit my backend and get any information I want. Basically, I just have to have my user and the service name, and then I can just hit the page just like that, as easy as that, right? But this is not what I want. I don't want someone just randomly come in and just hack into my system and look at it. And so we have network policies object to do this to help us to restrict the traffic. And in here, I have an ingress policies that look up the labels on my pod. And in here, I would say I would want all my pod that has a label X, in here is email service, to only accessing to this pod has label MySQL, right? So let's take a look at how we're doing this. And so I already label all my services the way I wanted it, obviously, when in the deployment. And then I will have a policies that apply to my namespace, which you saw on the slide, that describe what's the ingress, what's the port, and where it goes. And once I apply my policies to my namespace, then I will no longer able to hit my backend because the network policy is restricting my access to it. Basically, my label, where I'm running my PHP, the label doesn't match, and therefore you can't. But let's take a look at how we would do it when your entire application. If your application will normally have multiple namespace and multiple service and pods underneath, we want to deny all the service access for all namespace. Isolate your namespace first, and so there's no access whatsoever to start with. Then we will create policies around and specifically for the incoming traffic. And so let's take a look how we would do it. Oh my God. No one raised the hand, like, don't know what I'm talking about? All right, thank you. All right, I'll stay away from this thing. So I have a script that just running these policies across different namespace. And then right now I just, oh, I didn't touch it. Right? All right. Okay.
Can you remove it and put it back?
Oh no. So I set up the system. I purposely make a video and thinking, okay, great, nothing will happen. Sure enough, there's something, right? I was like, oh my gosh. So I have these policies that will look at the ingress traffic. I'm not allowing anything in, and nothing will be directing. And if I go to my application right now, I shouldn't. There you see. I shouldn't see anything because I isolated my entire applications, right? And then I'm not going to go through every single policies. Idea is that we created policies that has matching label, how we describe it in the policies. For example, in this PHP, I have a policies that allow 8080 coming into a pod that runs my PHP has a label that called app equal user reg, right? And then once I do that, I should be able to hit my login page. And then I will have all the policies that describe how my pod and pod communication within the namespace. And if you have policies that you want your services hitting outside of the namespace where your service is not the same namespace, then you will do things like this, that you will have a label for your project, and so your service is coming from this project, and this project has a label called projects equal to blah, 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 and then going into the port 8080, and then we'll hit that service that you want it to be. And then obviously I'm going to apply all the policies to it on all different namespace, because it's all around the namespace, and then you will be able to hit that application. Back to you.
All right.
Here.
So basically, from the example, what we have seen is, just to summarize, right? You can apply policies to restrict the traffic from pod to a pod within a project, from pod to another pod in a different project. So you can restrict the traffic to within a project or to outside the project. So network security policy is a superset of what multi-tenant provides, as well as a little bit more granular stuff that you can get, right? So with this, you can implement the dream of microsegmentation on an OpenShift cluster, right? Now let's move on. So we solved one problem. Next scenario. We did all this. Next thing is, I have from the my setup perspective, every enterprise has multiple security zones, right? Network security zones. So you have, for example, DMZ, where that's the only touch point for any traffic that is coming from internet, from outside your enterprise. That's where things like reverse proxies, load balancers, and web servers would run. And then there will be a firewall, and your application zone is firewall protected. This is just an example. You might have more than this, right? And maybe there will be a data zone where your data is hatched, which is again firewall protected. There is a double firewall. Now, holes are punched in these firewalls to allow traffic coming only from DMZ to app zone, and only from app zone to data zone. Now, if this is my setup, how do I run an OpenShift cluster in this kind of a setup? Do I run an OpenShift? Will the OpenShift nodes reside in one of the zones, all the zones? What do I do here, right? That's the next question. You have a couple of options here. One of the things you can do, if this is what is mandated by your security policy, is to have a separate cluster in each zone, right? Completely isolated OpenShift cluster in each zone. Again, this is not a recommendation. It is just what is possible if your security policy doesn't allow you to have an OpenShift cluster that goes across all 3 zones, then this is what you would do, right? But there is a headache of managing 3 clusters now, right? And also, it's not as simple as this, right? In the demilitarized zone, you have a master, you have all those URLs that you expose for log consolidation, for metrics and all that. You don't want these to be seen by the outside world. So you still have to protect those. So while this is possible, the maintenance is high here. So what are the other possible options? Think about this. We can set up a OpenShift cluster, right? And this OpenShift cluster can reside anywhere, but it is single OpenShift cluster across all the zones, right? Using network security policies that we already looked at, you can do microsegmentation. You can have your DMZ pods, applications that are supposed to run as DMZ, can also be running on this cluster, as well as the other zones. And if you want to separate them out, use network security policies on the same OpenShift cluster, right? That solves the problem to some extent. What about ingress and egress? That's where what you would do is set up infrastructure nodes, and these infrastructure nodes will run in the respective zones. And on these infrastructure nodes, you run the ingress and egress. That's how you can set up a single OpenShift cluster that works across multiple network zones. This is the recommended solution, right? Now, one of the things that we should remember is once we set up a cluster and you have a set of nodes, even if those nodes are spread out across all the 3 zones, let's say, as long as you open that port 4789, you have this overlay network, right? The traffic between the pods has nothing to do with your physical firewall. Because you open port 4789, all the traffic between the pods is flowing over the overlay network. So your physical firewall has no impact on the overlay network. So the only way in which you can do firewalling is by using network security policies. Got it? Right. Let's move on. So I talked about ingress and egress. So how do I secure egress? And then we'll get to ingress after that. First, let's understand how does egress happen. So if I have an external system that's running outside OpenShift, maybe this is a database or some other external service that an app running as a container on OpenShift wants to call. What are the possible options? One, the pod can make a call directly, but you are embedding the URL or the access point for your external service into your application itself, right? If that's the case, that means you're kind of hard coding into your application. The better way to do that is create something called an external service. What is an external service? External service, every service you know, and I was assuming that you know how service works, right? Service has a selector, and the selection mechanism based on the labels selects the pods that it is front-ending. If you have a bunch of pods, you create a service, that service has a section called selectors, and that selector section will decide which pods this service is going to front-end based on the labels that you would have put in there. An external service is a service where that selector is empty. So when a service gets created, it doesn't know which pods it is front-ending. So how do you tell that this service is pointing to an external system, which is outside OpenShift? You manually create.
Okay. I need a new laptop.
All right. So you manually create an endpoint behind the service. So usually the endpoints for a service are pods, right? Instead of a pod, you create your own endpoint, and that endpoint will point to the destination IP address, which is outside OpenShift. Now, you may have multiple applications that are trying to reach this external system. All they have to do is call this external service, and that will redirect it to the external system, right? Now, the advantage of this approach is if for some reason that destination IP doesn't know what's going on. If for some reason the destination changes, IP changes, this is the only point where you would change it, right? But you can also do this with a fully qualified domain name. It doesn't have to be an IP address, right? Create an external service, and endpoint can be FQDN. In both cases, when this traffic goes out of our cluster, how does your external system see this traffic? Where does it see it coming from? That depends on the node on which these pods are running. If you have a cluster with 10 different nodes, right? If the pod that is making this call is on node number 5, the traffic here is seen as coming from the IP address of the node. If the traffic is coming from node number 4, it shows up as node 4. Now, what if you had a firewall here, and you are restricting the traffic to come from specific source IP addresses? You don't open up the firewall for all the nodes in your OpenShift cluster, right? You might have 100 nodes in the cluster. So how do I set up my firewall that allows traffic only from specific IP addresses? That could be your use case. If that's the case, we would use this mechanism. This is called Egress Router. What does Egress Router do? Egress Router is a special pod. And every pod, our pattern is pod and a service in front of it, right? So egress pod is front-ended by an egress service. Now, just like that external service, this egress service is what is called by your application. So your apps can be running anywhere as pods on your OpenShift cluster. They'll make a call to the egress service. The egress service will redirect the request to the egress pod, and egress pod sends out this request. But it does a little bit of magic here. Your egress pod, when you bring it up, you'll set 2 different configurations in this egress pod. One of them is a source IP. The other one is a destination. This destination is your external system's IP address. The source IP is what you have opened up on your firewall. So if your firewall is allowing traffic from a specific IP address, that IP address is what is defined in this egress pod. Now, what this egress pod does is, irrespective of wherever the traffic is coming from, again it went up. Sorry.
Sorry, no,
Okay.
it's.
Maybe you have. Can you hold this like this? Oops.
I'm going to hold this laptop for the whole time.
Yeah,
Right.
that's good.
Like this.
Thank you.
All right.
Thank you.
I'm not moving.
So when the traffic goes out, it changes the source and to the source IP. So your firewall will see the traffic coming as a particular source IP. Right? That's the advantage of using the egress pod. But if I have so many different services, do I have to create so many different egress pods, right? What are the other solutions? We recently introduced in 3.9 this other solution where you can assign this egress IP at the project level. So if you're running n number of services within a project, all these services you don't need to create an egress pod anymore. All the services, when the traffic goes out of the project, it will get the same IP address, irrespective of where these pods live. So your project is created, but these pods can be scheduled on any node on the cluster, right? Irrespective of where those pods are, when the traffic goes out, since you configured the egress IP for this project, the traffic goes out with that particular IP address. So if you tap the traffic here, you'll see the IP that is configured here. The way in which it works is you will add an additional IP address on one of the nodes on the cluster, and when you configure the project, if this IP address is assigned to any of the nodes on the cluster, that node is what is used to NAT the traffic out. So let's say this pod resides on this other node. From here, the traffic will travel to this node because this is the node which has this IP address, and from here it gets NATed out. Good?
I'm going to demo this one.
So we have a demo for this one as well. Let's look at it.
All right.
Should I hold it?
No, that's okay. All right, just wink at me. I'm looking at this. If this was over, so I have a small system. I have two nodes, one master and one node. For this setup, I feel this is much more easier to implement than the egress router serving the same use case and same purpose. And so I have a project called Egress Project, and I have a simple applications running within it, and I scale it up to replica and each pod running on each node. Right? So, and then this particular application will just make a request to the external system that's showing at the corner, and it will show where the traffic, the source IP is coming from. And right now I have node 1 as IP 55, and then I have master 54, and then if I make a request coming from these pods, the request going to the external system will see that traffic, the source IP coming from as where the pod is running by default, right? Because you can have your pod running anywhere. And then you can see at the bottom, this is the where the pod actually running, and so you will see the source IP as that. And then similar to the other pod, it will show the source is actually coming from the 54 instead. But this is not what I want. I want them coming to the external system, see it as one single IP address so that my external system can set up a firewall that seeing the same traffic coming in, right? That's the purpose of it. And Veer explained it, so I'm going to fast forward a little bit, right? And I picked one of the node as a, thank you. You guys listening, very good. All right, so I have a node that picked the node 1, have an IP address 55. I just add another floating IP address that I have that to the same interface in the same subnet, right? And so this would be my static egress IP address that I'm going to use. So if you look at the host subnet for the nodes, there is no egress IP as yet. So the one that I picked, 34, I'm going to add that to my node 1 egress IP address and tell it I'm going to use this node 1 as the place where hosting my egress IP address, basically. And then remember the project name is Egress Project, so my namespace Egress Project needs to know where my egress IP address is, where my application is running. So I'll do a similar OC patch, and then I will add my IP address to the egress project, just like that, easy. And then you're done, right? So now, really done. And so here, yeah, so you can see the egress project has the IP address that I added to it. In this version, only one IP per project right now. So now I'm making the same call to my external system. I would expect that IP address from both both of the pod going into the external system to be the same. And sure enough, the 34 show up first, and then second, my VI search is not so good. Here. So you can see both of the IP that way. Then basically, when the pod is running on other nodes that's not hosting the egress IP address, what happened behind the scene is your traffic will then get routed via the VXLAN, your overlay network, to the node that hosting the egress IP address. And then it will get called to the external system. So when it gets to the external system, you will see the IP address where it should come from. So back to you. All right.
Thank you. So that was about using a static IP at the project level, right? Next, what else do we have? Can I restrict the traffic going out of my project? You can do that. There is something called an egress firewall to limit access to where your traffic can go. You can set a pod to talk to hosts that are outside, that are within your network but not to internet, for example, right? Or you can set policies like, my pods can talk to public internet but not to my external systems. Or I can control this at the subnet level. So my pods can talk to subnet A but not to subnet B or anything that is not in those subnets kind of thing. So you can set up your specific firewall rules at the egress firewall level to limit that access to traffic going outside. Now let's come to ingress. If you have used OpenShift, you all know about OpenShift Router. How does it work? Very quickly. So you set up OpenShift Router on one of the nodes. Typically, we set up an infrastructure node on which the router runs. OpenShift Router is a HA proxy load balancer. It runs as a pod. It runs as a privileged pod, and it listens to any traffic coming in on port 80 or 443 on the host on which it is running. So as long as you make the DNS setup in such a way that your URL that has to result to the application gets to this box on port 80 or 443, it will be picked up by the router, and the router will redirect the traffic to the respective pods, which could be anywhere on your cluster over the overlay network. We saw how the overlay network works before, right? So it uses the same mechanism. Now, can I restrict access to the route? I know that I can get traffic into my cluster using port 80 and 443, but how can I restrict access, right? That is where IP whitelisting comes into play. In the router configuration, you can set up IP whitelisting, and you can say that, hey, I'll allow traffic only if it is coming from these specific IP addresses to my particular URL. It's on a route by route level. When you create a route, you can set up this whitelisting, right? And then now we talked about port 80 and 443. That allows you HTTP, HTTPS, WebSockets kind of traffic. What about if I want if I want to run some applications that are not using port 80 and 443, and I don't want to expose those applications on 80 or 443, I want to use some other ports. In that case, you have multiple options. I'll discuss one after another. The first one is a node port approach. The first one is a node port approach, where you define, when you create a service, you define the type as node port. When you do that, what OpenShift does is when it brings up this service, it allocates a port in the range of port 30,000 to 32,767 on every node on the cluster. So one of the port numbers is blocked across all the nodes in the cluster. So when you make a call from outside, you can make a call to any node's IP address, either this IP or this IP or this IP. If you make a call on this port number, it gets redirected to this service, and from there the traffic reaches the pods. This is one of the approaches. But if we do this, how do I set up my firewalls? I mean, I have to open up my firewalls across all the nodes on the cluster for all these higher level port numbers. If you don't want to do that, right, what are the other options? Next option is to use type as external IP for your service. When you create a type as external IP, there is some administrative task to do here. It is not as simple as using a router. As an administrator, the administrator defines an external IP address range and assigns those external IPs to certain nodes in the cluster, right? Typically, these could be those infrastructure nodes. And those are extra IPs that are allocated to those nodes on the cluster. Now, when you specify the type as external IP and leave it at that, OpenShift will automatically pick up one of those IPs and add it to your service. Now, if you make a call to that external IP, it reaches the host for which that external IP is allocated. From there, OpenShift knows that, hey, if I'm getting traffic on this particular IP address, it is meant for this particular service. It redirects it there. And from there, it reaches the pods. Now, you can also leave it to OpenShift to assign the IP address from the list that your administrator would have configured. Or you can specifically ask for a particular IP as well when you are creating a service. Both options are possible. So this allows you to set up your firewalls to allow traffic to particular IP addresses for ingress. We talked about egress. Now we are talking about coming in. Now, you can also set up these IP addresses. What about failover, right? You can run IP failover, which also runs as a pod. Now, IP failover is available as a container. It runs as a pod, and that will automatically manage in case the node which has this IP goes down. You set up that IP as a virtual IP, and it will assign to some other node. That was about egress. Now let's go to the next use case, which is how do I secure? Now I know how to do ingress. I know how to do egress. I know how to set up a cluster in a multi-zoned environment. I know network security policies. What else? How do I secure traffic flowing between the nodes itself? OpenShift allows you to use IPSec, which uses OpenShift CA and existing certificates configured across your OpenShift nodes. Now, all the traffic going between the master and the node and the node is all secured with IPSec. So your traffic is encrypted. You will need 3 files: cluster CA file, the client certificate, and private key. These are all configured into LibreSwan database, and you can set up the policies IPSec. You know IPSec, right? Internet Protocol Security policies to encrypt the traffic between the hosts. Next, coming to the application level. We talked about the bottom levels, but what about the developers building applications, what they can do in terms of network security for the apps? We talked about the router and the routes, right? Can I do SSL for my applications? Absolutely. And there are 3 different possibilities there. One, this is the OpenShift router that we discussed before, right? You can not do SSL at all, in which case there is no problem. It goes all the way across to your application. But if you are doing SSL, you can have the SSL terminate at the edge. Our edge is the router. And the traffic from the router to your application, that means this is within the OpenShift cluster or the overlay network, that goes unencrypted. So from outside to your router is encrypted. From within OpenShift cluster, it is unencrypted. That is one option. The other option is you can use pass-through termination on your route, which means that router will not try to decrypt the traffic. It will just pass the traffic all the way to your application. The implication of this is that your application, application container needs to know how to handle SSL decryption. So your certificates need to be configured at your application level. The third option is to do re-encrypt. This is the case where you have cert1, which is between the client and the router, and between the router and your app, you use a different certificate. That is re-encrypt. This is how you will do SSL for your application traffic coming through the router. What else? The next question that we get commonly asked is about layer 7 application security. So I want to monitor traffic, the east-west container traffic within the OpenShift cluster. Can I do that? I want to set up web application firewalls. Can I do that? Can I do granular traffic control? Can I do packet inspections? Can I do things like denial of service? Can I detect the denial of service attacks or ransomware, viruses, and all that stuff, right? Or can I just do runtime security with forensics, capturing incidents, doing auditing, and stuff like that, right? For these, OpenShift by itself doesn't provide a solution from Red Hat, but we do have partners whose solutions have been tested. These are all listed on OpenShift's partners list, and you have a choice here. So pick your favorite, work with them, figure out what they have to offer. Each of these have their own benefits in terms of the kind of things that they offer, and you can select any of these solutions. All these solutions are containerized, and they work on the platform itself. So you have multiple options here. What else is coming up? In the area of application security, you would have heard this term Istio quite a few times in the past couple of days, right? Istio also has things to offer in the area of network security. And let's talk about it briefly. We have 10 minutes. OK, that's good. So the way in which Istio works is it uses a pattern called sidecar proxy. Your developers, your application developers, will build their code as containers, which has pure business logic and nothing else. They just have to take their business requirement, write their code, and create their containers. The rest of the things that you want to do for monitoring your applications or whatever, right, you can do by injecting this sidecar proxy into a pod. So you all know that pod can run more than one container, right? So your business logic container is supplied by your developers, and when the application gets deployed, you can automatically inject an additional container, which is called a sidecar proxy. What does this do? Any traffic going to your application container is intercepted by the sidecar proxy. If you're running multiple applications, let's say you are running 2 different microservices, and these are talking to each other, the traffic from this to this doesn't go directly, it goes via the sidecar proxy. So the sidecar proxy itself is forming a network across different applications that are running within your cluster. And this network that is formed by the sidecar proxy, these dotted lines, is forming a mesh network that is called a service mesh, right? Istio uses this service mesh. Istio is nothing but an implementation of this service mesh. So we have the sidecar proxies, and Istio uses Envoy. You know Lyft, which is this car company, they have developed this Envoy, and they donated that. So it's an open source thing, right? So Envoy is your sidecar. You have the mesh network, but in order to instruct your sidecars on what to do, you have an Istio control plane. Istio control plane includes a couple of components. One of them is a pilot. This is using which you are telling Envoy on what to do. So for example, using the pilot, you can send commands across your cluster saying, hey, if I'm getting traffic to microservice A, I have 2 versions of it. One is version 1, version 2, right? Version 2 is just added. I'm still testing it. So if the traffic is coming from this particular user Joe, who is a tester, direct the traffic to version 2. Otherwise, direct the rest of the traffic to version 1. You can send such a command using pilot. So you can configure the routing rules. What other things can you do? I have this newer version of service, but this service is being used by this new customer. I want to direct specific traffic that is coming from this particular customer based on the HTTP address to this newer service. All other traffic goes to the older service. You can configure things like that using the pilot. Pilot can talk to all the Envoy instances across your OpenShift cluster and instruct what to do. It can configure the routing rules. You have Mixer, which has where you can configure additional tools. So for example, you have application monitoring tools, let's say. You want to monitor the traffic that is going across the cluster, or you want to do log consolidation, or you think of anything, right? Mixer allows you to provides adapters where you can plug in your own tools Of course, those tools have to be built to work with Istio, right? So all the tool vendors in the industry would have to comply with this mixer's plug-in mechanism and build adapters to plug in their tools into the mixer. Using mixer, you will tell on what data that tool will need. So if you want to monitor traffic, what are you expecting to get? Those rules are configured into the envoys. Envoys are intercepting all the traffic going to your pods, right? So those will report all the data back to via the mixer to your adapter. So for example, think about App Dynamics. Today, App Dynamics or New Relic or any of these tools are built into your application. You take the jar file and you bundle that with your application. Tomorrow, you don't have to do that. You just put it here, tell Envoy what you want. That data is reported back to that via the mixer to App Dynamics or New Relic or any of these tools, and they can do whatever they want with that data. So your code remains pure code, green code, nothing else. It is clean. So that's the architecture that is coming up. But what about security part, right? From network security perspective, what can we do? That's the third component, which is Istio CA. The control plane includes that Istio auth, which has a certification authority. What it will do is it uses, how many of you know about service accounts in OpenShift? You heard of service accounts, right? Every pod on an OpenShift cluster runs as a service account. This concept has moved from OpenShift into Kubernetes. Now Istio is using service account as the identity for every pod. So using service account as the identity, a certificate is generated. It uses SPIFFE for generating the certificate, and Istio CA generates those certificates and distributes across all the pods in your cluster to your envoys. So now using these certificates, you can set up mutual TLS between the services running on OpenShift. So one of the things that we talked about is all the communications between the nodes can be secured by using IPSec. But not just that, now we are talking about any pod talking to any other pod, any service talking to any other service on the overlay network. Even that traffic can be encrypted using mutual TLS because you have these certificates distributed. Not just that, I want to revoke the certificates. Just go to the control plane, revoke the certificates. I want to add new certificates because they are changed. I want to change the secrets across all my applications or all the instances of my application. You can do that from the control plane. This is not there yet. It's coming up. But this is the future.